Good afternoon, everyone. I'm Francesca Bassi. I recently joined the links and I work at SystemX. And today I'm going to talk about a topic which is securing communications in the CITS. And this is a topic that we are working on at SystemX since quite a bit of time. Okay, I joined SystemX in 2019, so a part of the work has been done by my colleagues before. So I am part of a project. Maybe not all of you know how SystemX works. It works on projects, and the consortium of a project resembles people both from industry and academia. So this is the third project around these topics that we have at the Institute. And you have on this slide here all the logos of the partners of the consortium that works in TAM. So this is the outline of the talk of today. I'm going, as I said, to present you the problem, give you a broad introduction to the topics we are working on. And I will start briefly introducing CITS, which are Cooperative Intelligent Transport Systems. This is an acronym that stands for, well, everything that is a transport means which has embedded intelligence, so digital intelligence, and cooperative is for possibility of communication. So you have a figure here that gives you an idea of what we are talking about. So you have nodes, which are vehicles or pieces of infrastructure, which can communicate with each other. So you have that a vehicle may want to communicate with some infrastructure in the back end, or you have communication between vehicles and neighbors in what is called an ad hoc network. It's a network that is created in the immediate physical neighborhood of a vehicle. So in order to work well, you need regulations. So you need to get everybody to agree on what are the protocols, the kind of messages that you can exchange. And this is done in Europe by the IRT, which is the standardization body who is publishing the standards for communication in the CITS. So all the acronyms like V2V, vehicle to vehicle communication, V2I, vehicle to infrastructure communication, and so on and so forth, belong to this ecosystem and designate a particular kind of communication in this system. We are interested, as we said, we can identify two kinds of communication. The communication between a vehicle and some backend infrastructure. And this kind of communication is not so different from what happens when you call somebody with your mobile phone, or you read your emails with your mobile phone, and communications in the ad hoc network. So it's communication which is called short range because it's opportunistic in nature. I can exchange with anybody who is in my radius reach, and not with somebody who is farther away. And this kind of communication is what we are giving our attention to, because, as I said, the long range is very similar to standard communication, and so the solutions that apply to, for example, mobile communications may apply to long-range communication between a vehicle and the backend. There are two kinds of radio access technologies that are used to do this direct communication. The first one is called in Europe ETS G5, And it's a standard, it's a radio access, which is based, well, it's a version of Wi-Fi, which is tailored to the vehicular case. And the other radio access interface that you can use is based on the cellular radio access interface. So you have an LTE version, you have also an NG version. What we are going to talk about today is pretty much independent on the radio technology that you choose, so it applies to both. Just one word on the kind of messages that are standardized. So that you can exchange between vehicles. You have basically three kinds of messages in Europe. The first one is called the CAM. They are beacon messages. Every vehicle on the road is expected to broadcast information about their kinematic dynamic, so the position, the speed, the heading, and it is expected to do so in a periodic way. So 1 to 10 times per second, depending on the situation, on the context, whether I'm driving on a highway or in a urban scenario. Then you have messages which are called the DNMs. They are warning messages. They are not periodical. They are triggered by events. So a vehicle observes an event on the road. It can decide to propagate this information in the neighborhood. And finally, you have collective perception messages. They are almost standardized, but they will be standardized very soon. And these messages are periodical as the beacon messages, but they allow a vehicle to broadcast information about not themselves, but about other objects on the road. So these are the bricks that you are going to use to build your applications. And so the problem that we are approaching, that we are trying to solve is, how do we make the communication of this information secure? And in order to do so, we need first to define security. So you have a traditional set of properties that you need to satisfy in order to secure your communication system. And they rest on these properties are 5. They are listed on the slide. You need to provide authentication of the parties that want to get communicating. You need to provide integrity, to provide proof of integrity of the message that you are going to exchange. You need to guarantee no repudiation. That is, you need to give proof to the receiver that the message has not been tampered with, and it comes, this is integrity, that the message comes from the sender who declares to have sent this message. You need to ensure confidentiality. That is, I need to protect the content of my message. Nobody else can see what is inside. And you need to ensure privacy. The communication doesn't it shouldn't give away more information than the content of the message. So this is the traditional view, and we know how to ensure this, for example, in communication on the internet. When we consider the ad hoc vehicular network, things change a little, because, for example, we are not going to require confidentiality of the messages. The reason is that these messages need to be consumed by other people on the road with a very tight constraint in latency. I am going to broadcast my message, so everybody needs to hear it, and everybody needs to be able to consume it very quickly. I am working with an onboard unit which is limited in complexity, so I cannot encrypt my messages. My messages need to be delivered in broadcast and in plain text. So I'm dropping this requirement when I'm approaching communication in the vehicular doc network. And this is going to give me a lot of pain ensuring privacy, because in this way, well, I'm broadcasting information about my position, so it's really, really easy to track me, and it's really, really easy to profile me, and it's really, really easy not to be compliant with laws that protect privacy and data. So, well, given these requirements about security, how we do proceed to secure the communication, the first thing that we are going to do is to use a public key infrastructure, which is something that is very standard. And just, well, some words to recall what are the principles that are behind this. Any node, any vehicle who wants to participate in my system is required to sign the messages that it's going to emit. And so each vehicle is going to send the message in plain text, signed, and a certificate with their public key so that the receiver can verify the signature. And the certificate is going to be signed by a trusted authority. And so, well, by signing the messages, I'm going to ensure integrity and attribution of the messages. In order to do so, it's a PKI, so I need to have trust in the issuing authority, in the authority which is issuing the certificates and signing the certificate. So this is a scheme of the PKI architecture that is used for the CITS. We have a root authority, which is the ultimate source of trust. And then we have a series of authorities, which are called the enrollment authorities, which are the entities who deliver the pair of keys and the certificate to each vehicle which is born, that is to say, which joins the system for the first time. So in this ensures that only authorized entities can participate in the CITS system, which is good. On the other hand, if I leave an entity sign their messages with the same key all along their life, I am providing quite a powerful tool to track this entity in space. For example, imagine you are passing every day close to a street lamp, which is equipped with communication capabilities. It gets very easy to know that you are there on your way to work or something like that. So in order to protect the privacy of the users are not going to use these long-term certificates in order to communicate with other parties. Users are going to use short-term certificates, which are delivered by another authority, which beforehand verifies that the entity is actually enrolled in the system and provides the entity with certificates which have an expiry date. So I think a certificate may live up to 1 week in the, well, this is the time frame which is considered in the real world in applications in Europe now. So you have vehicles who might require a batch of certificates, short-term certificates to use to communicate with other people. And so with this infrastructure, we have a public key infrastructure that actually ensures the privacy requirement. So just just a small note on this. When I say privacy, I mean I cannot be tracked on a large scale. Of course, if I'm driving on a road and somebody is on the same road I am on, of course, this person will be able to know that it's still me, even if I change my temporary certificate during our driving together. Okay, so the privacy is with respect to tracking on a larger scale than the time I actually spend with somebody else on a road. Okay, so up to this point, with the PKI, we are able to authenticate and restrict access to the system to authorized party. Doing so, I can revoke certificates. So if I catch somebody not behaving the way they are supposed to, I can decide that the authority will not give them short-term certificates anymore, and so they will not be able to participate in the system. And I can guarantee that the messages that are exchanged are, well, I can guarantee integrity and no repudiation on the messages that are exchanged, and I preserve privacy of my users. But we are not done yet, of course. This is the question that I'm going to ask now is, what should I do to secure this communication system that the PKI cannot do alone? And in order to do so, I need to go and look at the applications. So I will present you some examples of applications. So in the first picture on the top, you have some vehicles on a road, on a highway. You have the orange vehicle, which is in a given position, and it is claiming to be in the shaded position. Maybe, yes, you see my small hand. It's claiming to be in a position which is not the real one. So on the basis of this message, of these beacon messages, the vehicle behind, well, it will reduce speed because it will sense an imminent collision. So I give false information and I change the behavior of the people on the road with me. The same thing I can do with a false event warning. So the orange vehicle is disseminating the information that there is a traffic jam ahead. So these two vehicles, they change the lane, they change their trajectory. And so that, well, I imagine that this guy wants to speed up on an empty lane. So both of these things I can do being compliant with the PKI system. So legitimate users can make a use of the system in a legitimate way, which is not consistent with the intended use of communication. So there are different class of attacks that can be done by legitimate users of the system. The attacks of giving away a different position with respect to the true one, it falls in the class of data injection attacks. So both of the examples that we saw in the slide before are this kind of attack, but there are others that can be perpetrated by legitimate users. One class is jamming attacks. Users are sharing the radio channel. So if one user decides to jam the channel, transmit very big amounts of information so that nobody else can succeed in communication, well, this is a disruption of the communication, and it's a kind of attack. that can be done by a legitimate user. You have physical attacks. For example, imagine, well, the example of a laser pointer on a camera of a vehicle produces false data, false sensor data that can be propagated around. And then you have another class of attacks that comes from the fact that in the system that we have built, one vehicle may have at the same time several valid certificates, and this vehicle may decide to use them simultaneously to fake traffic, like to give other participants the idea that more vehicles are on the road in a given time. So what we want to do with the class of techniques that goes behind the name of misbehavior detection is protect from attacks which are by legitimate users of the system. So yes, as I said, we call misbehavior detection this protection, and we need to be very clear in defining what it is a misbehaving station, because it's a very misleading term. So to us, when we speak about misbehavior detection, a misbehavior station is a station which is transmitting data that it should not transmit if the system was operating as expected. So there is a big focus on data. A misbehaving station is not somebody who is driving way too fast with respect to the speed limit. It's somebody who is transmitting data which is somehow false. So misbehavior detection boils down to be able to catch messages which are not correct. And our attacker model, well, our attacker is an insider, so it's somebody who is legitimate in the system, and who is active is somebody who is transmitting data. And this includes both vehicles who might be malicious, operating some kind of attack, or vehicles who might be faulty. They, I don't know, they have a faulty sensor, so they are broadcasting information which is not at all true. Yes.
I have a question about it.
Yes.
Active attacker model. Cannot we have also a passive right? Because, for example, a node may not broadcast some messages that it should do, or it may not also send warnings. Why we would expect to send
this is still active. This is still active in this classification. Passive is like it would be somebody listening to the traffic and then using this information for a malicious end. In this case, not transmitting something that you are supposed to transmit is still considered active. So in order to understand why we
perhaps another question. So what about, I mean, just other type of jamming, not by users which are legitimate, but I come with a transmitter with high power on the frequency which is used by either type of communication. So does it belong to any of the classes that you?
I mean, it's an attack and it disrupts the system, but this is not something we are looking at, because in the end, and it will be clear, I hope it will be clearer later, in the end, what we want to do is to be able to alert the consumer of information that the data that they got is not trustworthy. And well, I jump ahead. The idea behind that is that you imagine a system where you have some kind of automated driving. Okay, so what we usually say is that communication is just one sensor more that you should fuse well, the data of which you should fuse with the onboard sensors, which is true, but there is another aspect of it, which is I can make rather sure that my onboard sensors have not been tampered with or they are functioning in the proper way. I cannot be so sure about communications that come from other parties whom I don't know. And so the focus here is on securing the messages that come from other people. And if I have a jamming attack because somebody put a transmitter there and I cannot communicate, I have a disruption of the system, but this is not falling under the misbehavior detection definition, because I cannot, the consequence is not, I can say that this station is producing information I should not be trusting in this moment.
Thank you.
Okay, so just to illustrate a little bit more, this thing which is important to understand in order to understand why we are consecrating time and effort to this problem, I have a series of applications. I have like 3 slides where I am going to show you what you can do at application level using communication. So you have a class of applications which is called usually by the industry day one applications or driving awareness applications. And they are based on the fact that vehicles broadcast beacons in a periodic way. So here in the figure, you have 2 vehicles which are transmitting the beacons. At a given point, this vehicle is going to brake. And thanks to the periodic beacon, this vehicle here is aware of that. And so they can brake. How do they brake? Well, you have a signal that is alerting a driver, or you can have some kind of automatic control in the braking. But in this case, for day one applications, you have a driver in the car. Another application, always using the another example of application using the beacons is the one that you have in this figure. So you have 3 vehicles, 1 to 3, they are emitting their beacons. Vehicle 1 wants to turn left. Vehicle 3 is speeding in the intersection. And since, well, vehicle 3 is not directly visible by vehicle 1, but they are communicating their positions and their heading. And so they both know that if they do not brake, they are going to collide, and so they safely brake. In this example, we jump to day 2 applications. And the difference is that now a vehicle can transmit information about themselves, but also about any other object they see on the road. So the vehicle has sensors, they perceive objects, and they broadcast the map of the objects they see. So you have vehicle 1, who is going to go forward in this intersection. You have vehicle 2, who is not stopping at the red light. And you have vehicle 3. Vehicle 1 cannot see vehicle 2 because there is an object between them. Vehicle 3 can see vehicle 2 and can broadcast this information so that vehicle 1 is aware of vehicle 2 and can stop. This is still an application where you are supposed to have a driver, a human driver behind the wheel. So if something doesn't work as expected, there is a human driver who can take a reaction. And then you have applications which are called day 3 and beyond, where you start having the assumption of automated driving or semi-automated driving. So in the end, you will not have a human to react if something goes bad. And the example that you have here is a maneuver, a blind merge. So there is this vehicle 2 who wants to change line or lane, and he needs to negotiate. He needs to negotiate the lane merge with vehicle 1 and vehicle 3, who need to make space for them. And so vehicle 2 can negotiate this and safely change line if everything is as expected. If errors in communication happen, and if no human driver is there to correct them, this is a situation where the malfunctioning of the system may have a potential impact on safety. And so this is why protecting this exchange of information is rather important, and it will be important in the future when we will see more of this kind of applications, automated driving applications. So before, well, yes, we introduced the problem of reaction. Of course, I can make the assumption that I am able to detect a message which is malicious, a message which is misbehaving, which is not true. So in use cases that we can see nowadays, use cases where you have a human driver, you can say to the application that consumes the data, do not take into account data that comes from a source which is not trusted, and you are safe. You can continue driving. In the future, if you interrupt communications, you are going likely to disrupt the task that you are trying to accomplish, or you are going to compromise your safety. And so, well, this is a topic of some importance for these reasons. So this is what happens when you reason in terms of local reaction. So what happens in the vehicle when I detect misbehavior? We have another level of reaction, which I'm not going to talk very much about today, which is the global reaction. So we are building systems where vehicles who are aware of misbehavior of other parties may report this misbehavior to a backend entity, a backend authority, which will collect enough information to ascertain what is really happening is actually misbehavior. And if it is the case, may ask the PKI to revoke the certificates or not to deliver further certificates to the culprit. So you can take an entity and you can remove it from the system if you have the certainty or that they are not legitimate. So very quickly, I'm going to go through a list of the local misbehavior detection techniques that we can use, because so far we didn't really go into that. So I call it local misbehavior detection because this is something that needs to happen on board in the vehicle or in the infrastructure and the street lamp. The input of this process are all the incoming messages, all the sensor readings, or all the contextual information that I might have. I might have a map of the road I'm traveling on. And the goal is to identify misbehavior. That is to say, identify wrong messages and their sources. So I have two classes of methods. I have data-centric methods and node-centric methods. So data-centric methods focus on the trustworthiness of the data, while node-centric methods try to evaluate globally the behavior of the transmitters. So in order to be able to detect misbehavior, the thing that I will be forced to do is to go into the semantics of the messages that I'm exchanging. And this is what makes this exercise different from standard intrusion detection in information systems, right? So when I focus on data-centric methods, I'm going to look into the semantics of the messages, and I can verify their plausibility. And in order to do that, I need to assume an underlying model, which usually will be the law of physics. If somebody is telling me they are traveling at 500 kilometers per hour, of course, I know that they are not really driving that fast. And these methods can be performed by each station on any incoming message. And of course, they will be as efficient as the word model I'm assuming is accurate. Of course, if I can build in context, if I can say to my station, okay, I'm driving in a city to 100 kilometers per hour will be not plausible, but it would be on a highway. So I have several examples listed here of what I can do. I can check the strength of the signal in order to verify if the claimed position in the message is plausible or not. I can use prediction of the position of the vehicle in the following second in order to call the plausibility of the message. I can validate the message that I receive with my sensor perception, or I can validate that the position of somebody claiming to have having observed an event is compatible with this event. I can do the same exercise by checking the relations between multiple messages and multiple sources. So in this case, I can still do this exercise on any message, any incoming message, but this time I need to have a honest majority around me. If everybody around me is lying and is lying consistently, I will not be able to catch this lie. And some examples here are position overlap. Of course, two vehicles claim to be in the same position. One of them is lying. I can compare data coming from different stations. For example, perception of a vehicle, a perception message of a vehicle compared with the, I don't know, beacon of another one. And as before, post-event detection falls within this category as well. And then I have the second class of methods, which are node-centric methods. They want to express the trustworthiness of the node, and from the trustworthiness of the node, I may deduce the trustworthiness of the data that comes from the node. And I have a class which is a class of methods classified as behavioral detection, and these methods are the closest to what it is done in traditional intrusion detection mechanism, because they do not descend in the semantic of the message, but for example, they consider metadata as the frequency of the messages in order to decide whether a node is behaving or not, while behaving or not. And the example that we did like half an hour ago, a node who is supposed to send beacons but who is not, falls in this category. And then finally, you have trust-based detection. And in the exercise that you are trying to do is look at your neighborhood. You have nodes. You want to assign trust levels to all of them. And this can be done in several ways. One way you can, I'm going to like explain 3 ways you can achieve that. The first one is the centralized trust model. So you assume you have an authority somewhere in the backend, and this authority is logging what happens, is maintaining a trust table of all the entities that you have in the system. And when you encounter someone for the first time, you query the authority for the trust level. The authority gives you this centralized trust level, and then you behave accordingly. And in order to do so, you need to have peers that mutually evaluate each other and send in upstream towards the backend this information so that the central authority can maintain this global trust level. So this is very efficient because the central authority has the ability of seeing all the data which is produced in the system. And on the other hand, is a system which is not feasible or very difficult, feasible with well, challenging, let's say, because you need to have enormous amount of data in uplink and downlink, and you need to satisfy near real-time requirements in the downlink when you request the trust level of somebody whom you don't know. So this is present in the literature. It's not likely to be the solution we will see in real time. On the other hand, you have a process where the trust is maintained locally. So I encounter other vehicles. I start tracking their behavior. For example, I evaluate every incoming message from this specific vehicle, and I decide it is trustworthy because during the time we spent together, the data seemed legitimate. So you can do this, any node can do this, these operations, so the requirements and the assumptions are basically, well, no assumptions required. On the other hand, you are able to gather a very limited amount of data with, because the time you are expected to spend with other entities is very small. So you will not have enough time to consistently build your trust level in others. And the data, it's only the data that you see, only the data that you receive. So in order to have a solution, a compromise solution, you can consider cooperative local trust systems, where every station is maintaining the trust level in the neighborhood, but you are also allowed to circulate your trust table to your neighborhood. So a vehicle can base their own decision of trust level on their own data and also on the decision that other people took on the same vehicle. And this allows you to, well, increase the number of data you can factor in your decision, and also to increase the permanence of the network, because you will mitigate this phenomena where neighbors appear and disappear very quickly, because neighbors are neighbors of neighbors. So you reach farther, basically. This is on the feasibility side. This is much more feasible than a centralized solution, but still it will require ad hoc protocols for exchanging the trust level the trust levels in the neighborhood. These protocols and this kind of messages do not exist in the sense that they are not standardized yet. So this is a research topic and not yet an implementation topic. But this is the most promising solution. So I will conclude with the last slide. And the title of this slide is the title of a PhD thesis that we are going to start in the TAM project. It's Cooperative Trust and Misbehavior Detection in Cooperative Driving. We are going to consider these topics in the context of these cooperative driving applications like platooning. It's an application where vehicles form a string and they drive together for long periods of time. And this is interesting because this allows to decrease the distances between the vehicles and to make economies in fuel, for example. As an horizon, platooning has a leader. There is a special node who is the first node in the string, but we are starting thinking about applications which are fully distributed where there is no node who has a special role with respect to the other. And we are looking at these applications because they are cooperative in nature. So to accomplish the task, the vehicle needs to cooperate. So we are, it comes in a straightforward manner, the fact that they need to cooperate also to perform misbehavior detection and to maintain trust. And the good thing about these scenarios is that vehicles stay together for longer with respect to a standard driving scenario. And so this will give us the chance to explore a lot about trust. And so we have identified a series of problems that we will have to tackle for these applications. And the first one is how I do establish trust in somebody I do not know when I decide or when I'm evaluating the possibility of joining a platoon or forming a platoon with them. Then how do I establish and maintain trust during the operation of this cooperative task, the platoon in this case? And then how do I collaborate to perform misbehavior detection for all the time we are going to spend together? This is to protect against attacks, but also faults. And then how do I react within the application if I decide somebody is not behaving as expected? And then finally, how do I report what I see? And so I will stop here, which is just about leaves us 5 minutes or so for questions if we have some. So thank you.
Any questions in the room? Yeah.
Yes, so you talked about detecting misbehavior, but only from one user at a time. Do you think about Byzantine faults, or maybe when it comes to an attack, to several users that try to attack at the same point and try to falsify the
Yes, you will always have some assumptions that you need to make. So if you assume they federate themselves to attack you and they are enough, well, at a given point, your strategies will fail. And the thing is, yeah, try to develop strategies and explain which are the limits. And yeah, of course, it's a risk.
Other question?
Perhaps I have a couple of questions.
Yeah, go ahead.
Yeah, the first one is about the, these questions, when you have a fixed topology, have been discussed, right? So there is this Byzantine type of problems where when there is a proportion of misbehaving nodes, which is large enough, things do not work, and if it's small enough, then you can correct things. So the first question is, so here the main novelty, if I get it correctly, in you ask the same type of questions, but the topology is changing, right? And you have everybody has his or her environment at any given time. So you have a very dynamic version of the topology of the graph, right?
Yeah.
And so, but there is another thing also, which is the radio nature of the links, right?
Yes.
So yeah, I mean, the two questions are, I mean, can one phrase first the problem in terms of the specificities with this radio and nature of the link, plus the changing topology, so as to pose problems like in these classical problems of trust in distributed systems for fixed topology. And so, I mean, it's new, and the framework is different. So can one just, I mean, state a model where one can pose the question of I mean, so a typical question indeed, if you would have some sort of homogeneity, would be that if there is a number, again, a proportion of liars which is small enough, then you can correct that by whatever means, right? So, but it should be dependent on the assumptions that you take on the motion, on the homogeneity of the network, and on the
kind of messages as well.
And the radio nature of the exchanges, right? So.
And I don't have an answer in the sense that we are not done with modeling the problem yet, because we are really, well, not even started with this PhD thesis, but it's very interesting. Yeah, maybe in a few months I will meet you again with the model.
Yeah, but so what would be interesting is to add the radio nature of the links, because I mean it may be that some of these messages simply don't make it, right? So it's neither lie nor
but if the messages do not make it to us, it means they fall out of our neighborhood. So it's a vehicle going farther away, and so we cannot reach them anymore.
Yeah, but it could be very local, right? So it could be it's because of interference. If there is a radio link, there is fading or interference, and then the thing, so
it could be, yes. We for the time being, we didn't factor this in, and I agree with you. It would be very interesting.
Okay, right. I see. Yeah.
And then I mean, there you start to have differences. You start to be dependent on the radio access that you use, because in one case you have reservations of your resources, like kind of scheduling, and in the other not. So yeah, it's very interesting. So thank you. It's a very interesting suggestion.
Okay, thank you.
Yeah, I wonder about the role of infrastructure, for instance, edge computing in this kind of stuff. Because the problem of trust here is that I have to trust cars that I've never met, so I don't know if they are trustworthy. And you talked about decentralized.
This might be
entity, but the problem that you mentioned is that we have to transitate a lot of data to a central server. This problem doesn't hold anymore. I mean, if we keep roadside units, they are like the police, the authorities, so they sign messages that we can sign.
Yes.
And then they are there, so they can verify geographically that the messages are plausible. So
they can verify, and I mean, the idea is for a passing vehicle, the vehicle passes a roadside unit. The roadside unit knows if they are there, and so they can say these are trusted guys. But this vehicle might start to a civil attack, And so the only thing I can verify is that the beaconing of the position is correct, which is something, but it's yeah, it's not all. As I see it, this is a very interesting way of protecting against faulty equipment, because, well, I can relax the real-time requirement. The only thing that I want to do is to make sure from time to time I check that everything is in order, your sensors work fine, and so I can protect I guess in an efficient way against that. I'm not really convinced it is effective against attacks, and of course, using multiple local authorities might solve the problem of uplink and downlink. But then, once again, I will have to broadcast lists, and if I do it in EPS G5, I'm using the small channel that is allocated. So on the other hand, if I can do it with a backend, maybe I can do, I don't know, mobile network unicast, and I can go on licensed spectrum. And so I can leave the spectrum for direct communications. I don't know, there are all sorts of engineering problems.
Other questions?
Perhaps one more on my side, if you allow me.
Yeah, sure. For me, it's
Yeah. So so there are engineering questions, but I think there are also very interesting legal questions.
Yeah.
I mean, so could you say a few words on how people envision this improvement of security with, I mean, in case of, as we have seen for the autonomous case, but it could be now in the V2X case when you exchange these messages and assume there is an accident. I mean, who is liable? Are these those who designed the system? Or what are the thoughts?
I totally see the problem. I do not have a reasonable point of view because I'm not well versed in the regulations, and yeah, so it's a capital problem. But I do not know what will be the outcome of this discussion. And on the other hand, I'm pretty sure that we need to make sure that when you consume data that you received, you can trust them. And I think there is no ambiguity on this point. So for the time being, I sit here.
Yeah, but so my point here is that we are in a very different framework compared to, so I think the mindset which you describe here is that of, I mean, nodes which would be in a network would have no identity, but cars, I mean, they have a number, right? So, which is
no, nodes have an identity, in fact.
So, sorry?
Nodes have an identity. They are transmitting, they have a signature. Even the temporary signature can be traced back to their permanent identity. The only thing being, I cannot do it myself. There needs to be the intervention of the authority in the PKI to be able to link the two. But in case of, if I need to investigate an accident, I can trace back the identity, the permanent identity of the sender, of the station who sent.
Okay, so in that sense, I mean, the problem is very different from this Byzantine thing. I mean, if somebody acts as a criminal, so he will be sued as a criminal, right?
Yes, but
kill somebody
real
not real time, but I mean, justice is always, fortunately, justice is not real time, right? So, okay, so there are specificities. That's one of the important points of this, the radio link, the fact that in that case, users have a physical identity, which is not necessarily the case of the assumptions of these Byzantine problems, right? So, so yeah, the legal aspect may have different dimensions there. So, Okay, thank you.
Thank you.
Last question.
Connected remark about privacy versus trust, in a sense that everything needs to have a name, everything needs to be broadcasting their name, be it a temporary name or permanent name. Probably you can collect, harvest, and trace everybody's life or movements or thanks to this kind of approach. Can you comment on this first?
Yeah, the whole pseudonym or temporary certificate infrastructure is done such that it is not possible or should not be possible to trace people on a scale which is larger of tracking people who are driving with you on a road. Of course, you can use a pseudonym and change your pseudonym, but if you are driving in front of me, I will know it's still you. I will be able to link your two pseudonyms, but this will not be possible for a piece of infrastructure who is seeing you going one way in the morning and the other way in the afternoon if you changed your pseudonym.
Not even having a camera?
Having a camera is having a camera and harvesting data, which is not radio data. So
Yeah,
here,
together with things, so you can basically associate one picture which is very from a picture and a picture which is from radio data.
yes,
Okay.
but this is a problem that is not specific to this application, in the sense that I can do the same thing, associating your face to your, I don't know, cell phone number when you pass by a book.
Well, my cell phone number, I'm not broadcasting openly.
Well, your Wi-Fi MAC address. I think this is what the advertisement companies use when you pass by those totem with.
If you don't turn it off.
Yeah, if you don't turn it off, yes, of course. But yeah, what I'm meant to say is that this is not more dangerous than anything else you do in real life. The idea of the pseudonym is to minimize the risk that you incur using communication, and the rest, it's risky.
Thank you.
Thank you.